All right, guys, we're going to start section 7.5, which deals with exponential functions. So previously you evaluated numerical expressions involving exponents. Now we're going to talk about how to graph exponential functions and identify data that displays exponential behavior. Those are the two concepts we're going to focus in on with these video lessons for this section. So new vocab you're going to encounter are exponential function, an exponential growth function, exponential decay function. We're going to get into that. So an exponential function is a function of the form y equals a times b to the x. So in this case, the variable is the exponent. A and b are numbers. And it says here that a can't be 0 and b has to be greater than 0, in other words, positive, but not 1. Okay, so a can't be 0. If it was 0, you'd have 0 times whatever this b to the x was, and it would just always be 0. So you don't really have too many exciting things happening there. But a is not 0. It can be positive or negative. But b is positive, but not 1. Okay, so it could be like 1/3, 1/4, 7/8, 1.729. It just can't be 1. Okay. Notice that the base of the exponent is a constant. That's what b is. And the exponent is the variable. Exponential functions are nonlinear. Remember, linear has the word line in it. Also has the word ear, but not focused on that. So if it's nonlinear, that means the graph does not end up being a line. So an exponential function is a function that can be described by an equation of the form y equals a times b to the x, where a is not 0, b is positive and not 1. So here's some examples. Y equals 2 times 3 to the x. Here the x is understood to be on the 3, and the 2 is multiplying that. Here y equals 4 to the x. In this case, the value of a would be 1, like this. Okay, and same thing here. It'd be like, you could think of it as y equals 1 times 1/2 to the x. Alrighty, so those are just some examples. Now, if I want to graph y equals 3 to the x, we can make a table. I'm also going to find the y-intercept and state the domain and range. So if I make a table of values, I like to pick some negatives, 0, and some positives. So if I put in -2, it's going to be 3 to the -2 power, which is 1/9, or 1/3 squared, which would be 1/9. If you put in -1, it's 3 to the -1, or 1/3. If you put in 0, remember any number to the 0 power is 1. If you put in 3 to the half, you get about 1.73. If you put in 1, you get 3 to the first power, which is 3. And 3 squared is 9. If I plot those points in a graph, you'll see that they go up in a curved manner. All right, so you want to graph the curve there. So the graph crosses the y-axis right here. And really, to get the y-intercept, you just plug in 0 for x, which is right here. So the y-intercept is 1. The domain is all real numbers, because you can put any number you want in for the exponent. And the range is all positive. So the domain you could write like this, x such that x is all real numbers. And the range is y such that y is greater than 0. Okay? Because no matter what you put in, even if you put in a very large negative number, like 3 to the -15, or 3 to the -15 million, you're going to get an answer that's really, really small, but still positive. All right, so there you go for that one. Notice that the graph approaches the x-axis, like it levels off at the x-axis, but it actually never touches it. So there's not going to be an x-intercept. And if you look at the graph, remember we read graphs from left to right, just like you read a book, and the graph is always going up. It starts off going up slow, and then as you move across, it gets steeper. All right, so let's graph 7 to the x. We want to find the y-intercept and state the domain and range. Go ahead and pause the video. Okay, we're back. So first thing we got to do is make a table. Put in x, 7 to the x, and then the y value. So I'm going to put in -2, -1, 0, 1/2, 1, and 2. Okay. Now, if I put in -2, you get 7 to the -2, which is 1 over 49, which is about 0.02. So that's really close to 0, but not quite. If I put in 7 to the negative, if I put in -1, that's 1 over 7. Which gives me about 0.14, which again is really close to 0. If I put in 0, 7 to the 0 is 1, so it crosses right here at 1. If I put in half, 7 to the half, that gives me 2.6. So a half is about 2.6 right there. If I put in 1, that's 7 to the first power, or 7. Should be right there. And if I put in 2, 7 squared is 49, which is way up here. So the graph looks like this. Okay. The y-intercept is 1. The domain is x such that x is all real numbers. And the range is y such that y is greater than 0. Okay? All right. Hope that was helpful to you. Now, functions of the form y equals a times b to the x, where a is greater than 0 and b is greater than 1, are examples of what's called exponential growth. Notice that the b value is bigger than 1. They all have the same shape as the graph in the two examples that we just did. They have that curved shape and they're always increasing. Functions of the same form, but where b is between 0 and 1, are called exponential decay functions. So, and they also have the same general shape, but it's not exactly the same as the growth model. So we'll go through an example right here. If I want to graph 1/3 to the x, find the y-intercept, state the domain and range, what I'm going to do is make a table of values. And here I just picked 3 just to make it quick, but you have -2, 0, and 2. If I put in -2, 1/3 to the -2 power is 9. 1/3 to the 0 power is 1, and 1/3 squared is 1/9. Now be careful, when you are entering these numbers into your calculator, make sure you put the fraction in parentheses, then do the exponent. Okay, if I graph those 3 points, it's going to start here, then at 0 it's going to be at 1, and then at 2 it's at 1/9. All right, so notice it has that same general shape, like it's curved, but now it's decreasing. Okay. The y-intercept is 1. Again, the domain is all real numbers because you can put any number you want in for the exponent. The range is all positive numbers. But notice as x increases, in other words, as you move from left to right on the graph, the y values decrease, but they start off decreasing really fast and then begin to level off. So here's one for you to try. I want you to graph y equals 1/2 x to -1. 1/2 to the x power minus 1. Now here, when you make your table, you want to do 1/2 to the x power, and whatever that answer is, subtract 1 from that. Okay? And we're going to find the y-intercept and state the domain and range. Go ahead and pause the video. Okay, we're back. So I'm going to pick -2, -1, 0, 1, and 2. All right. Now, so this is going to be 1/2 to the x minus 1, and then our y value. So if I put in -2, you get 1/2 to the -2 minus 1. Be careful how you put that in, and that will give you 3. So -2 is up here at 3. If I put in -1, you have 1/2 to the -1 minus 1, which would give you 1. So negative 1 is at 1. If I put in 0, I'd have negative 1/2 to the 0 power minus 1, which gives you 0. So right here it's at 0. If I plug in 1, you get 1/2 to the 1 power minus 1, which is negative 1/2. So right there. And if I put in 2, you get 1/2 squared minus 1, which is negative 3/4, which would be there. So what this graph is going to do is going to decrease and actually level off at negative 1. So the y-intercept is 0. The domain, again, is x such that it's all real numbers. And the range is y such that y is greater than negative 1. Okay, so here's what happened. This minus 1 shifted the graph of the exponential function down 1 unit. Okay, so normally exponential functions just level off at 0. They level off at the x-axis. But since you had that minus 1 subtracted from the exponential function, shifted everything down 1 unit. And now the range is everything greater than negative 1. Okie dokie. All right, the key features of the graphs of exponential functions can be summarized as follows. If you have exponential growth, you have the same function, but the value of b has to be bigger than 1. It can be a fraction, it can be a decimal, but the value of that fraction or decimal has to be greater than 1. The domain is all real numbers, the range is all positive real numbers. Now remember, if you add or subtract a number from that exponential function, then it's going to shift it up or down. There is one y-intercept and no x-intercepts of the regular one if you don't shift it up or down. And as x increases, y increases, and as x decreases, y gets close to 0. For decay, it's kind of flip-flopped. The equation has the same form, but the value of b is a value that's between 0 and 1. The domain is still all real numbers. The range is all positive reals. And again, you have to take into account that might change if you're adding or subtracting a number off of the exponential function to shift it up or down. There's going to be one y-intercept and no x-intercepts, again, unless you shift it up or down. The end behavior is as x increases, the y value approaches 0. So as you go out, the y value gets close to 0, but never actually hits it. Again, but you also have to take into account if the graph is shifted up or down. And as x decreases, the y value gets very, very large. All right, so exponential functions occur in many real-world situations. The function c equals 179 times 1.029 to the t models the amount of soda consumed in the world, where c is the amount consumed in billions of liters and t is the number of years since 2000. Graph the function. What values of c and t are meaningful in the context of the problem? Now, this one's going to be a little bit weird to graph by hand, so we can use a graphing calculator, and I'll show you how to do that. So notice if you turn your graphing calculator on, whatever stuff you have in there, you can clear it off. Make sure you just clear anything else off. And make sure you enter it as 179, parenthesis, 1.029. Close your parentheses and raise it to the t power. Now it's going to put x in here because the calculator always uses the variable as x. So don't be scared by that. If I hit zoom 6, that's going to give me the standard viewing window, okay, which is just goes from -10 to 10 on the x-axis as well as the y-axis. Nothing's there. Why? Well, when you graph it in that viewing window, that graph doesn't show up because it's outside of that viewing window. First thing you can do from there is hit zoom and go down to zoom fit, which is choice 0 on this calculator. So what the calculator will then do is it will automatically calculate a viewing window that will help you see more of the graph of the function. Now this one, it's kind of hard to see. It looks like it's a line, and I think what happened was they zoomed out far enough and set it up that you're just seeing such a small piece of the graph that it doesn't really look like much of a line. But if we change the window to the one that they set up, where they said they went from -50 to 50, and that they scaled those by 10, and then the y goes from 0 to 350, and they scaled those by 25. Now if I graph it, it's going to look a lot more like their graph. Okay? Now, think about this. What values of C and T are meaningful in the context of this problem? Well, what do C and T represent? C represents the amount of soda consumed, and T represents years. So, since T represents time, it makes sense to think about T being greater than 0. At T equals 0, the consumption is 179 billion liters, which means that's how much they started off with in the year 2000, because T is the number of years since 2000. Therefore, in the context of the problem, C is greater than 179 is also meaningful, okay? Because time really doesn't make sense to think of negative time, so C values for negative values of T aren't really going to be of much value in this problem. So how much soda was consumed in 2005? Well, on your calculator, what you can do is hit second, calculate. Number 1 is a value, and you just put in 5. And for the x value 5, the y value is 206.5. Or you could evaluate the function at 5 by hand and plug in 5 here. And then, so you'd still have to do it on the calculator. 179 parentheses 1.029 parentheses raised to the 5th power. And you get 206.5 that way. Well, what does that mean? Well, in the context of the problem, the C values represent how many billions of liters, and the T values represent the years since 2005. That's why I didn't put 2005 in here. I just put 5, because T represents the number of years since 2000, not since 2005. Right here. Okay, so when you put 5 in, you get 206.5. So in the context, that's 206.5 billion liters of soda. All right, here's one for you to try. Go ahead and pause the video. Okay, we're back. A certain bacteria population doubles every 20 minutes, beginning with 10 cells in a culture. The population can be represented by the function b of t equals, b equals 10 times 2 to the t, where b is the number of bacteria cells and t is the time in 20-minute increments. How many will there be after 2 hours? Okay, so a couple things. Notice that the value that's being raised to a power is 2, which is greater than 1, so this represents growth. Okay, so if it's growth, as we go out in time, our answer should get larger. So if they're telling us that it started with 10 cells, as time passes, our answers should get larger. Okay, now here's where the trick is. It says B is the number of bacteria cells, T is the time in 20-minute increments. How many will there be after 2 hours? You don't want to just put 2 in for T. Okay, so B equals 10 times 2 to the T power. You don't want to just put 2 in here because T represents the number of 20-minute increments. So really, if you put 2 in, that'd be 2 20-minute increments, which is only 40 minutes. How many? So you have to figure out how many 20-minute increments are in 2 hours. Well, 20, 40, 60 would be 3 20-minute increments. And that's 1 hour. Okay, so that's 1, 2, 3 20-minute increments in 1 hour. So if I want 2 hours, I'd have to use 6. So B equals 10 times 2 to the 6th power. So you have 10 times 2 to the 6th power. And that would be 640 what? 640 bacteria. Now, it just says that B is the number of bacteria cells. So put cells on there. It's not the number of bacteria cells in thousands and millions or billions or trillions or hundreds or anything like that. It's just 640 bacteria cells. There we go. All right, guys, that's it for this video. The next one's pretty short, so stay tuned for that one. See you there.